today we read the AFS paper, which is I think a very important paper, especially since we use AFS on our campus, right? How many of you use AFS? Okay, good. Even though I think Notre Dame tries to kill AFS, they've been trying to kill it for a longest period of time, but we still seem to use it, right? So this paper is sort of old, it's 88, and this describes AFS, or AFS, how it was back then. And so after that, Al Spector is not as a co-author here. He was a co-author in the original paper. He was a faculty at CMU. Then he went on to IBM. So IBM was trying to make this into a distributed file system. They had a product out for a long period of time. I'm not sure what they do right now. So there's a commercial version of AFS, and then there's the open source OpenAFS server, which kind of keeps on living, right? And partially because I think it's it met a lot of the goals that there are no other file system which kind of does that, right? So it's designed as for scalability, right? From day one, it was designed for scalability. It was designed to scale as much as 5,000 users at CMU campus, which when they built it was a pretty large number, right? I think they had 400 desktops, but they foresaw that eventually every student at CMU, every person at CMU would have a desktop. So they want a file system which can span that big a space, right? Which in retrospect sounds like a small number, but it's still, I think that, still it's one of the larger distributed file system. It's since expanded to a global system, so you can actually have AFS, so you can access AFS from any different site, right? So you can access your Notre Dame AFS if you go to another AFS location like Stanford or something. So you can actually look into here or what have you, right? And so some of the reasons that it was able to do that is based on their design decision. From day one, it was designed to scale, designed to do a whole bunch of stuff. And it was designed to work with heterogeneous clients. And they use, they have the weird way of naming stuff like Vice and Virtue and Venus and stuff like that. But they have notions of volumes and cell servers and what have you, right? How many of you used AFS from another site from Notre Dame or from another site access Notre Dame AFS?
Do you got like CRC? AFS?
Yeah, CRC is local. Yeah. You could, if you can just go to /AFS and then look at the different directories and then try to go in there. You should be able to see some public contents and stuff, right? I want you to try it because you will experience one of the things that is good or bad about AFS, which is when you first do LS, it'll be excruciatingly slow, right? If you go to another site, it'll be excruciatingly slow because a whole bunch of stuff will be caching to you. But after that, it'll be pretty fast, right? So the first time if you do a /ls of /AFS, it'll take you forever and ever to get the results back. But then things get cached and then things move along, right? CRC, you probably won't see that. You may not see that because somebody's actually using it, so it's always cached in your machine, right? And it's local to us, so it's distributed, but it's not that far from us, right? So these are some of the goals of what they wanted to build AFS for. I mean, this is the design goals that they had for building AFS. The first is location transparency, right? They wanted the same namespace for the system wherever you are, right? So what does that mean compared to, say, NFS? Do you think NFS supports name transparency? And what does it mean for AFS? Yeah.
AFS stands for like an Andrew file system. And so what your question is?
So my question is the location transparency, right?
Yeah.
So how does it relate to NFS? Does NFS provide location transparency? What does it mean for AFS?
AFS means like a network file system. AFS, what what I know in AFS, there's like a name resolution, and there is it uses lots of caches to
lots of caches?
Yeah, to store the.
What do you mean by lots of caches?
To accelerate the speed to kind of data.
Okay.
AFS.
What's okay. So in terms of name location, location transparency, do you see difference between AFS and NFS?
I think AFS is part of maybe it's a special kind of NFS.
Okay.
I know there are only two file systems in computer network, the NFS and SM. In Windows, it's called I think there are nearly two
Okay.
file systems, NFS and
So you guys read the paper, right? I didn't see the reviews from both of you, so I want to make sure that you read the paper so you can follow along, right? So these are important topics. So if you haven't read it, read it before, whenever, right? So you had your point.
So I would say there's no location transparency in NFS because you can mount the NFS server's exported directories wherever you want in a local file system. And each machine may have a different mount point, and the user has no way of knowing if they're looking at the same files without looking at the mount.
Yeah, NFS basically, it's up to the client to decide what the namespace has to be, right? And most system administrators I know try really, really hard to keep the same namespace. They don't want to mount the file systems on different machines in different fashion to confuse you. They want to have the same name. So if you go to the lab, we try to have all your home directories in /home or what have you, right? So it's easy for you to remember where you are. But that has to be done at the client end. So as a client, you have to know the location of where the file storage is, and you have to know the location of where the namespace has to be and how to glue them up, right? And with the AFS, the model was, since it's going to be scalable to a few thousand machines, they don't want it to be on the client side. They want it to be global. The system knows about location transparency. It's not something that you have to do, right? The second goal is the user mobility, right? User mobility, users should be able to access the files from any machine, right? Are these goals the same or are they different? Right? The first goal is you have to have the same name on any machine. The second goal is you should be able to access the files from any machine. Are they same or do they have to be same or can they be different? Or does this imply this or vice versa, right? Yeah.
Well, it's like what Nate was saying with NFS. Like in NFS, you can access them from any machine too. But the question is, they don't have to be transparent. Just because you can get at it from any machine doesn't mean that it's going to be mounted to the same directory.
But if you have this, do you get this? If you have the same name on any machine, do you get this?
If you can see the file but you cannot read from it, then just due to access control problem. Yeah, and it can actually be even worse, right? It can be such that you can have the same name, but the name may not be seen on every machine, right? That's also possible with this model, right? It can say whatever is in your laptop will always be accessed as /AFS/Nathan/file, right? So that's the name wherever you go, but that doesn't mean that you have to be able to access it, right? So you can log into a new machine. You won't be able to access his files. You won't be able to see that his files are there. But if you could, it'll be on the same name, right? So this one says that the name for a particular file is the same wherever you go. This one says that you should be able to access it from any other place. If you don't have this, that means you won't be able to access it, but if you could, it'll be the same name, right? So they don't have to be the same, but they can be different, right? So it's not always enforced, right? So if you go to /AFS in our space, and if you go to some of the, say, I know some Duke servers, right? From Wizard, you can't access those because I think some of the configuration, you don't have to show all the root stuff, right? because you don't have to talk to all the different cell servers because there's overhead. So the system administrator can say you may not be able to access /AFS/acpub.duke.edu just because there's no real reason why you should look at it, right? So they can turn it back on, but you don't really do that because otherwise you're keeping. So you could potentially have access to all the AFS file servers throughout the world, but the system administrator can decide not to have all those, right? But you're not allowed to have /acpub.duke.edu, even though we don't see it, right? If you could see it, it'll be in that location, so you're not allowed to clear that name, right? Does that make sense? So you could see it if you wanted to, but you don't have to see it all the time, right? And security, right? Security was very important at this stage because compared to NFS, where it is designed for a LAN setup, right? Where security is not such a big deal because the network itself sort of gives you compartmentalization within a certain physical space. So if you're using it on a LAN, and the LAN tends to be fairly small, so if you can keep it within this room, some of the security aspects of it, you don't have to worry about it. Whereas when you talk about a global system, or at least a campus-wide system, you can't trust all the machines, so you have to have some sort of a different security, right? So one of the security that difference between, do you know what the difference between security of NFS and AFS? You might have faced it in some sense, yeah.
You say AFS is user-based, with Kazar and NFS is more host-based security. Right?
What do you mean by that?
The NFS server exports file systems to allows the host name to do certain privileges of read-write, where AFS has permissions on directories and files and based on username of the authenticated user. So
there's two things, right? So one is the notion of who can mount and how they can mount it, right? So when you mount it at the server, I can say your whatever IP address you have, that IP address can mount it as read, write, or some of the different options, right? So suppose I'll let you mount it, right? So once you mounted it, right? What is the security that NFS uses and what's the security that AFS uses from your experience of using it in campus? Yeah.
NFS is usually mounted read-only. Usually use it to provide files. If it's mounted read-write, then it's on machines that are in a home directory. Because once you have that, you can do anything you want. The NFS server doesn't check. Other than read-write, you can do whatever you want to that file system. But on AFS, I mean, each call is verified by AFS in terms of creating a file or doing configuration.
Is that the difference? How many of you use AFS using Kerberos? How does Kerberos play into this picture, right? You must have used Kerberos, right? And if you use explicitly, if you leave yourself logged on for a while, something must happen, right? Yeah.
Something expires.
Yeah.
Zero access to file system anymore.
Yeah. So with Kerberos, you get a token, right? So with Kerberos, it does not trust you, right? The AFS model is it's so large, the system is going to be so large, so it doesn't trust the local machine at all. It doesn't trust anything that the local machine says. It only trusts something that it provides, right? So it has this complete set of its own authentication, its own authorization mechanism, which is not dependent on what you do, right? So you can log in as Nathan on your laptop, but AFS doesn't care what you're logged in as. It only cares about what it knows you as. The way it knows who you are is through its own authentication servers, right? So it uses Kerberos. So essentially what it says is you have to talk to the Kerberos server. Kerberos server will make sure that you are who you are and give you a token, right? And that's essentially a mechanism to cache your credentials, right? So it says, okay, I get these tokens. Then you can give the token back to me. Whenever you talk to me, you have to give me the token. And because of this, the mechanism that Kerberos uses, I don't have to go back to the server and ask to see if it's still valid. I can use it for the time that you gave me, right? So whatever time the token is valid, I can trust you, right? So you can give the token to somebody else if you wanted, and he can give me the token for service, and I'll give it to him, right? So I don't particularly care who you are. All I care is whoever has the token is the one I trust. And I know who the token to be trusted because I know it's all running Kerberos, and only Kerberos can give me the token I want, and we are good, right? Whereas in NFS, he trusts the client, right? Meaning he does not have its own authentication. It trusts who you are. So if you say you are Nathan, I trust you, right? And the way you say you are Nathan is you give a user ID, right? So with the NFS, if you say I am user ID 100, I give you all the files that belong to user ID 100, right? So what's bad about the NFS model? Yeah.
If you have a shared directory and a machine is compromised, does it trust the host? Anyone on that machine can do whatever they want to that process?
Yeah, I don't impose anything about user IDs, right? There is nothing which says what user ID you should be, right? So I, as a system administrator for the server, can say whether I trust your host or not, but I have no way of knowing what you do as user ID, right? So if I give you if I let you use the machine, and you choose yourself a user ID of 100, you will read and write whatever was allowed for user 100, right? You don't have to. So there is no notion of a user name. It's only a notion of user ID, which I don't control in your machine, right? So can you think of one reason why this is super bad idea? What if you could choose any user ID? What user ID would you choose to do bad things? Yeah, root, right? Root is 0, right? So if you choose yourself a user ID of 0, which I have no control over it, right? You can become whatever you want because it's your machine, right? So if I trust your machine, and if you become root, then if you come to me and say I'm user 0, then Unix semantics would mean that I, as a server, have to give you permission to all of this stuff, right? And clearly that's a dumb idea, and clearly why the servers do not trust the user root. So if any of you who manipulate with the NFS stuff, right? By default, it does not trust the user root, right? User root does not trust because there's ample reasons for mischief. So I can override it, but by default, I don't trust it. But there's nothing which prevents me from doing anything else. So if you don't trust you want to see what your friend has, right? There's nothing in NFS protocol which prevents you from creating an account on your machine. All you have to do is make the user IDs match as your friend, and then that's it. You get access to all the files that they have. As long as I trust your machine, you have no security, right? So in a lot of sense, NFS security is like really inadequate for machines that I don't really trust, right? I have to trust the machine. I have to make sure that you do the right thing. Otherwise, it's very easy for you to just change yourself to some other user and then see all the files, right? So if that is the case, why do we still use NFS? Yeah.
It's really easy to set up, and it gives good performance for a small number of users.
Yeah, it's easy to set up, and it's easy to. For a small setup, it's kind of okay, right? So if in the class setting, if any of you change one of the stuff, I know who to come and hit back, right? So it's sort of okay, right? If it's used throughout the campus, you can't expect somebody to be keeping track of all the stuff which is happening, especially on a global scale, right? So the security model means that I don't trust the client. All I trust is I trust Kerberos, which comes with AFS, right? It doesn't have to be Kerberos. It could be something else, but it's basically something that I can trust. So you have to authenticate with something that I trust, and then you have to tell me who you are with every stuff, right? So it doesn't matter what you can become on the machine. I don't really care what you are on the machine. All I care is do you have the credentials which I get from somewhere else, right? So this way, I can potentially have a truly global system. So if I wanted access from, say, Stanford, right, I have to talk to the Stanford folks. I have to ask them to give me an account. Once I give an account, if I can then I can log into the Stanford Kerberos servers, right? And that can give me a token. So then I can use a token to give you access anywhere. So you can be on Notre Dame, and then you can have access to Stanford and Notre Dame, right? And the system would let you access it anywhere on the planet, right? There are a lot of practical reasons why it's not always feasible, and a lot of reasons why it's not actually used, right? Have any of you tried using that? The ACL model does not really let you specify some other site because you have to add all those stuff, and it becomes hard to maintain, manage, and all those things. So it's rarely, if at all, used in that way. But there's nothing in the system itself prevents you from doing that, right? So you could actually collaborate with anybody across the planet and just get credentials on all the different servers, and it'll work because it doesn't trust you. It only trusts whether you can log into the system, right? And the other goal was the performance should be good enough as you would see on a desktop, right? And we'll see what the decisions they made because of that in a little bit slides. But essentially, you want the performance as good as a desktop, right? And because of these goals, they have to make some compromises, and we'll see what they are in the next slide. And it should scale to thousands of users, right? I think they got it up to 400 when they wrote the paper, but clearly we believe that because obviously it works for NerdM, obviously it works for all these different sites, so it scales. I mean, whatever decision they made scales. They had other goals too, which is one of the things that you deal with when you have a distributed system, right? I forget who said that. One of the best comments about distributed systems were the mark of a distributed system is when you can't get your work done because of some server that you never heard of is dead, right? When you have distributed systems, it depends on a whole bunch of different stuff, so you don't want the failure to stop you, right? So you always, you get mail that OIT is bringing down some server or whatever. You would like the system to keep continuing as long as what you depend on is running, right? So if you have your home directory, which is on AFS, and that particular server is running, if you have the authentication server running and certain number of servers that is needed are running, you should be able to continue to work even though your friend may not be able to access it because their particular set of services are gone. So it has to be compartmentalized so that you can get good availability. There's no way the system can give you availability when your services are down, if your own file server is down, but otherwise you can still continue to work because if you don't have this goal, you cannot build a global system because essentially you can build a global system, but that won't work, that won't be operational all the time because one or the other server is dead, so the whole system has to stop, right? And the last goal is that users should feel good enough about it that they don't want to take backups. You want the users to be trusting enough of the system that you have to believe that something is being backed up, something is being done to what your data content is, because otherwise people will take backups and defeat the whole purpose of the system, right? I'm not sure how well they solve this or what is unique about this approach to solve this problem, but this is a goal that they had, right? And of course, it has to be heterogeneous because you cannot build a distributed storage system if it can only work on one architecture, right? And we saw that from NFS, and it makes a lot more sense here because since you're talking about a lot of nodes, you expect it to work across different set of architecture. So. Yeah, and the trust model is none of the workstations are trusted, and everything is encrypted based on the tokens that you get from a Kerberos server, which I trust. There's nothing magical about Kerberos, it's just that that's what they chose. And essentially, I don't trust you, all I trust is whether you have the tokens to talk to me. So they have a notion of WISE, which is the stuff that is trusted. So they have a set of trusted servers as trusted components, which somewhere lives in the cloud. And then you have a set of stuff that run on your client, right? The process that runs on your client is called Venus. And the concept of U is called virtue. In the original paper, they call this vice and virtue. Virtue is the one that you trust. Vice is the one that you trust. Virtue is the one that you don't trust, right? They had all these kind of names, right? Actually, forgot where it came from, but there's some reasoning behind it, right? So in order to scale, one of the important things we need to learn about what they did was it does several things. One is it does whole file cache, right? So and the way AFS is described here, it only does whole file cache. Of course, the newer versions they relax it a little bit, but the classical AFS will only do whole file cache. Meaning, when you access a file, you are required to cache the whole file and operate on it. You're not allowed to operate on the server itself, right? So you have to download you have to cache the whole file, and then you operate on it. In the original AFS, which is not the paper we read, right? All caches are validated when you open a file. Right? So when you open a file, you ask the server whether the cache is still valid. The way you do that is you look at the modification times, right? So what happens is when you open a file, you're required to make a copy and then operate on it, right? So the local file has a modification time, a server file has a modification time, right? So when you open the file again, not this version of the AFS, but the original AFS, which is actually published in 85 SOSP, you would verify whether the cache is still valid by asking the server whether the modification time, and if you see the modification time on the server is newer than what you have, then the cache is not valid. If it is older, then the cache is still valid and you use it, right? And with that model, every time you open a file, you have to ask the server, something, and that was kind of becoming a bottleneck. So what they did here is change it such that you only so they introduced the notion of a callback, right? And we'll see what it is in a little bit. But essentially what happens is when you don't actually ask the server what happened, the server now keeps track of who has what content, and then it'll tell you whether the cache is invalid, right? So when you ask a file to be cached locally, the server keeps track of it, and then whenever somebody else does something to it, it'll send you a cache invalidation through a callback. So when you open a file, you have to see whether you have a callback on it. If somebody else has done a callback, then you go and ask the server for new content. So you avoid you asking the server all the time. You avoid this polling all the time by essentially making the server tell you when things are done. So the original AFS was not as stateful as what they had to implement. But this saved a whole bunch of accesses, because one of the Berkeley studies said you open up a lot of files, small files, so you don't have to go back to the server all the time. So unless something gets modified, you get to keep the local file, right? And the other important stuff is when you open a file for modification, right? On close, your modifications are sent in its entirety to the server, right? Till you finish your modifications, none of these updates are sent to the server in any form, right? So the way you modify a file, you try to modify a file, which means that you have to cache the whole file content locally. Then you do all the operations locally. When you do a close, all your modifications are sent to the server, right? And the server then knows who else had the copy. So it'll send a callback message to all those servers to say, invalidate the cache entries, or rather, call back to all these files, right? If somebody else had already opened this file on another machine for read-only, they will continue to read whatever copy was left over from before, right? These callbacks are only checked when you open a file. So when you open a new file, this callback would mean that you have to get the new contents, right? There's a whole bunch of different concepts, and so let's see what happens, right? Let's say this person is writing a file, and let's say this is time, right? Time goes this way, right? This is 1 and this is 2, right? So this is read only and this is read only, right? So what would happen is when you open this file for write at this time, right? This user 1 will get a copy of the whole file, then they make modifications, right? Now user 2 comes here and they try to open the file read only, right? What version of, so let's say this is version 0 over here, right? So what version do you get here?
0.
You get the version 0, right? You get the version 0, and essentially you come up, you have the file open till here, right? And at this point, you go to version 1, right? Because you did the modification. You tell the server sends a callback. So it sends a callback here saying callback for this file, right? So what happens to this user?
The server tells the user to invalidate the cache.
Yeah, so what happens?
And then the user had to go and then grab another copy, which is version 1.
Is that what happens? So are you saying that at this point, when I get the call back, I flush the copy, I flush this copy, go back to the server, get V1, so I get V1 here? I mean, we know that over here you're reading V0, right? You read V0 till you get the callback, right? So when you get this callback, from then on, do you continue to read V0 or V1? AFS only checks callbacks at open, not after the open, right? So since there is no open here, you will continue to see V0, right? So if you try to open the file back here, again, this particular user, at this point you'll see V1 because when you open this file, you see there's a callback, that means you flush the stuff. You don't flush the cache here, right? So this write would not be seen by you till you open the file again, right? Is that clear? So you don't see these updates, you only see it, so the future opens will see this copy, whereas this read would have seen the new copy because when you open it, if the copy was there, it would have been flushed, it would have been called back. If there's none, you'll get the server things from the server again, right? So if you look at it from this time perspective, right, this client at this time would be reading the older file. This client at this time would be reading the newer file, even though they're both operating on the same file read only, right? Both the clients won't know what's going on because there's no way for them to know what's going on. All they know is when they read the stuff, you get a consistent view of what you're seeing, but when you're done, it gets flushed and you get the new content copy, right? Actually, there's no proactive system. So when you see a callback, nothing ever happens. Till you do a next open, the server does not proactively get a new copy or something. So you'll continue to have this old copy for a long time, but when somebody else comes and does a new read, you get the content, right? What that means is if there was 1 year goes by between these two events, right, you still have an old file and a callback. You don't capture all the output. So if you are a client which only read a file once and you never ever read the file, it may be in your local cache, but there's no network traffic trying to keep the cache contents consistent. All it means is whatever cache copy you have is no longer valid, but there's no active work done to clean up your cache. It just left there, right? So this is what you get, right? So what would happen if another user starts to there's a write here. At this point, what version do they get?
V0.
They get V0, right? And let's say they create V2 here, right? So what would this user get? I think it's after this, right? They'll get V2, right? Right? So what happens if this was, they started the operation here? If they started the operation here, finished it here, what would this get and what would this get? Right? This write started way back here, ended here. This write has started here, ended here, and this, and so on, right? So what do you get here? You get V1 here, right? What do you get here? V2, right? Because that's the latest step, right? So this protocol is called last writer wins, right? So AFS model of consistency is it follows a last writer wins protocol, right? Which means that you can have as many simultaneous writers as possible, as you want, but essentially whoever does a close the last, whichever writer does the close the last is the copy which gets to survive. Everything else is lost, right? So there is no way, there's no mechanism within AFS to make sure anything about here, right? So you could have come in and here modified whatever, but those are all completely lost with no trace because essentially whatever is the last one will survive, right? If you have a file open for read, then you continue to read whatever you have, whatever you had when you started, right? So this client would have started to read V1, even though for this operation, it would have no concept that there ever was a version called V1, right? Because if you look at this user, right, they would have seen V0, they would see V2, but they never saw V1. They don't know what V1 was or anything, right? From their perspective, they only see V0 and V2. From this person, they will see V1, even though these two have no way of saying what they saw. But that's how the system works, right? So this model is excellent for a number of reasons and may not be so excellent for some number of reasons. What are the benefits of this model, of this last writer wins model, where you know only close? I mean, when you do a write and you do a open a file for write and you do a close, only then do you talk to the server, right? Other times the server may send you a call back, but other times it doesn't do anything, right? What are the benefits of this approach? Yeah.
The protocol is pretty simple in the sense that before the client writes, it doesn't have to do anything. It doesn't have to check with any other methods. It just writes and transmits the changes back. So it doesn't have to check with all the other users using it. Wow.
Yeah, so a protocol can be very, very simple, right? What about performance, right? What about scalability performance on the server? Do you expect fewer interactions with the server or more interactions as compared to NFS, right?
Fewer.
Because, I mean, you don't really talk to the server, right? I mean, it's for the most part, you are basically a local. So for this user, right, for the user number 2, there is no reason why their performance should be any slower than a local file system, because this is cached, right? So all the reads and writes here are cached. They'll only do a flush at this point, right? At this point, they get a callback. So the only difference for them compared to a local file system is at this point, they have to get the new contents from the server, right? All these operations, after you do the open, all the operations are local, right? So if you open a file for write, the only difference between local file system and your file system and the AFS is when you do a close, you have to send something to the server, right? Otherwise, during the write operation, during this operation, it's basically a write to a local file. All this is basically to write to a local file. So your performance at this time should be as good as what you expect from a local file system, right? AFS should not slow you down. The only point it slows you down is when you finish your write, at which point you have to upload the whole file back to the server, right? And once you're done that, you're done. And for a read client, right, only when there's a callback do you see anything, right? So suppose you have a file that only you are operating on, it's not shared, right? And you are doing lots of reads on it, lots of reads and writes on it. How do you expect the system to work? If you are the only user on a file system, on a particular directory, what are the times you interact with the server?
It's minimum. You only talk to the server when you open and close the file.
Do you say when you open the file? You don't have to say anything when you open the file, right? You don't get a callback for your own. So if you're the one who wrote, so you don't get a callback for this node, right? So when you finish a write, your write will go to the server. The server will send a callback to every other node, but not to you because you're the most recent copy, right? So if you just take the case where there is one client which is doing a read and one of them is read, one of them is write kind of thing, right? So if this is a read, right, you open the file, there's no callback, so you're good to go. When you do a write, there's no callback, you're good to go. When you finish the write, you send a message to the server, you send the whole file to the server, but the server does not send a callback to you because you are the most recent version anyway, right? So this cache is still valid, so you don't have a callback. So compared to a local file system, if you are the only one who's using it, all this is local because there's no interaction with the server. You only interact with the server when you do a close, in which case you send the whole file to the server, but it doesn't have to stop you, and then all your reads are local, right? So for a single user, your system performance would be as good as what you see for a local file system, except with the caveat that you send something off to the server, which is a good idea because it's essentially you're sending it to a system which could be where it could be backed up and stuff. But essentially, this is what happens, right? So what happens if your client dies halfway through the transaction? Right. So here I did, this is a read, this is a write, and this is a read, right? What happens if the server dies, if the disk crashes, if the disk of the client crashes and you lose the disk?
Changes are lost.
Yeah, it's lost. I mean, it doesn't even try to get this stuff, right? So your hope of maintaining any kind of reliability is if you keep closing. If you don't close the file, if you open the file and leave it open all the time, then essentially whatever change you do is on your disk and it's lost, right? So how does this whole model gel with the Berkeley study, right? Files are small, they are read all from start to end. They're not really shared, right? How does this fit into that model, right? Yeah.
Pretty well, because if the file is large, you don't want to read an entire 1 terabyte file off the server before you start operating on it. So the idea of the whole file cache is very consistent with the Berkeley study.
So do you don't think this works well for 1 terabyte files?
Well, at least in this version, it doesn't seem to. I mean,
well, why
it wouldn't work any worse than NFS, but if you're reading the whole file. But
so if you're operating on a 1 terabyte file, right? What is not good about this the whole file caching decision?
You have to wait until it was cached before you could operate on it.
Yeah, so you have to wait for the whole file to trickle down to you, right? Well, I mean, what other sense would it be bad?
I mean, if you're only modifying 5 bytes in 1 terabyte file, and you have to write it back, creating a lot of disk and network traffic to do that.
Yeah, so the cost to upload your changes could be significant, right? But if you're using it like this, right, where you don't actually, not much sharing, right? System is okay because, so you'll send this 1 terabyte file here, unless you do some kind of compression or something here, but you're basically sending a 1 terabyte file here. But you get to keep this copy forever. So if this 1 terabyte you have will get you good performance. So it doesn't really hurt you as much until you begin to share, right? Until you have multiple users sharing these files, right? When you have multiple users sharing, how many of you used AFS to share contents with somebody else actively, not Dropbox kind of thing? Okay. You said, did you say yes? Did you say yes? Did you say yes? Or?
Well, I share stuff with other people, but we don't like modify. It's like, at the same time.
Okay.
So.
Yeah, so I'm saying like, yeah, share meaning like actively sharing, right? Like the Dropbox model, which is what most of us use, right? So basically you go to the Dropbox for the course and drop off your report, then I pick it up later, right? There's no sharing, but how many, like, have you done one of these things? I forget his name, right?
Oh, well, I mean, a lot of programs don't allow it, so it's kind of hard. Like, you can't open a spreadsheet and open Office 2 at the same time, and that's...
so how does it do that?
Well, it creates a temporary file or something that says this file is open, and then it checks
so how would you ensure that only one person can operate on a file in AFS in general?
You have to check with Vice on the server to see if someone has opened it, right? I mean, I'm saying that the editor, the program you use to edit it, is the one that enforces that, so it's hard to do, but in the file system, I guess you'd have to keep track of who has it open and in what capacity.
Even that becomes tricky, right? If you're using the file system to lock some programs by creating a file, right? Which is things you mentioned, right? So if you're going to modify a file, while you're modifying a file, you write the file, right? Even that particular file will have to go through the AFS model, right? In terms of when somebody sees the stuff. So you need to, so what would you have to do for the lock file, right? If you were to do this locking mechanism by essentially writing a file to the file system to say, I'm going to modify this file, right? So I think typically what would happen when you use your Excel or something, right? Excel would open a file, read all the contents, right, and then close it, right? And then it'll let you modify all the contents, and then it'll at some point it'll say open, right, and write your modifications and close, right? This is typically what applications do. Rarely do they open and then leave it open all the way here, right? So you want to prevent somebody else from modifying something in the middle, right? So how would you? So one of the things you mentioned was you create another file, right? You create another file, right? Let's say you open a file. You create another log file, which a third application, when it comes up here, if it sees this file, it's not supposed to do anything, right? How would you? Is there something special you have to do? Because all of them are in AFS, right? So is there something you especially do for this file, which will give you the log semantics that you want?
You'd have to open it and close it both right when you created it, so that it gets flushed down to the server.
Yeah, so you need to close it as soon as possible, right? Because once you close, so you could actually do this before this, right? You open the file and then you close this file, right? Because till you do the close, nobody else would see what you've done, right? Would that solve the problem? Actually, this has to be here, right? So here I do open, and then I do close. Would that work?
You should open it again once you close it.
Why?
So that another application can't delete the log file. So that that you have, so that the callback is, so that you've started the callback process.
Yeah, so what happens if two people did the same thing at the same time, right? If both of you did the exact same thing at the same time, right? Somebody else did this open, somebody else did this close, right? They'll also go through, because there's something which prevents them from doing that, right? So just because you do a close doesn't mean that you got it, right? And so you say, I should try to read it again to see if it is still valid.
Yeah, you might have some data in there that identifies that you created the log file, so that some hash or something, so that you know that it's your log file. If you open it up and it's not your log file, then something has happened and you didn't create the log.
Would that solve the problem?
No.
What if somebody opens a file here and then closes it here? The log file, right? So you'd open the file here, you were diligent, you closed it in 1 second. Then you try to read the file, you have the same content. This person also opened at the exact same time that you started to write, but they're just a slow person, so they took 2 seconds to write it, right? And when they're done it, they go read the file again. They see the contents, they'll see the contents that they wrote, right? Because last writer wins. So they would see the contents that they wrote. So they're going to be happy and they're going to be happy, right? So this brings us to a notion that we'll see on the next lecture, which is the notion of logical clocks and all those things, right? These things are really a painful thing in distributed systems, regardless of what AFS does, right? The notion of 2 concurrent events happening and the notion of serial ordering and all those things, which seems so intuitive to you when I talk about this in terms of like drawing these graphs on the board and say these 2 are happening at the same time, seems so logical. But in distributed systems, these are hard to implement because there are no communications like what we do here. So here we can see the global state of the whole system, right? With my eyes, I can see all of them at the same time. So I can say, oh, this happens before this, right? But in this distributed system, you don't know when things happen unless somebody sends a message. So unless you send some message from here to here, this does not know what happened, and so on and so forth. So what you're trying to do may not have the impact that you wanted. So if you're trying to do a log file, it may not do what you think it should do. It'll do something that is it's in a serial order, which we'll see in the next lecture, which is a very important concept, right? For the most part, it may not matter, right? People don't really open Word on 2 machines at the same time and try these things, so it works for the most part. But the AFS consistency model affects everything, including the log kind of mechanism, right? So there is a possibility that what you think is locked, it may not be locked, right? But no, none of you have really collaborated with somebody else, right? So none of you have worked with somebody else on another machine, right? Using AFS. Have you run distributed programs where they write So you wrote a program which runs on more than one machine, which all use the file system to communicate with each other, right? So you have one machine here, you have your process here, you have a process here. This process writes something here, and you expect it to read, right? Have you done that? Which is sort of what you did for the open office, right? You're writing in one machine, reading from another machine, right? Have you done that accidentally or by design? Accidentally meaning you started to do something on one machine. So you have your desktop and a laptop, right? Are you doing, or you log in here, you do a make, and you're trying to run the program from here. Have you done this? Like, because you don't want to be on the same machine, so you go log into one machine, compile your program, and then run it on another machine. Have you tried that? Because that is something that many people do, right? You kind of log into different machines and try to run the program, right? Or if you're working as a group project, your friend may be on a different machine. So you say, oh, I finished compilation, now run your program, right? So if you've never done any of this stuff, then you're fine, right? AFS will give you all the performance benefits that you wanted. I mean, now you're getting the almost local file system kind of performance, right? But if you do any of the things that I talked about, any of the things that you, in terms of sharing and all those things, then you have to understand what the semantics are and how these things work, right? So what do you think of last writer wins semantics? Is that something which sounds intuitive? So one of the things that they argue in the paper is that is intuitive, right? If you know what I'm talking about, it's intuitive, right? I think that's the argument they give. This is a perfectly intuitive solution because it's obvious, right? How many of you knew this before taking this class? I mean, before reading this paper? Was it obvious to you? Is it like so? Ignoring that you are computer science graduate students, right? Assume that you are C programming 101 class, right? And they want to use AFS. Can you explain this to them, or do they think they will understand? Without talking about partial ordering and all those things that we'll see in the next lecture. And going beyond that, would the secretaries, if they're doing this stuff, would they understand what this file system is doing, right? Yeah. You had something?
Yeah, I don't think it's not intuitively obvious in terms of the file system. I mean, if you explain how to access one user, then it's not a big deal. But I don't think it would be easy to explain to people how. I mean, you could draw it on the board, and if you do a diagram like that, then perhaps people would understand. But just to explain, like, oh, be careful, last writer wins.
No, I don't think you really understand by me drawing on the board, right? Because of the reasons which are on the next paper you read, right? The reason is, when you look at it from here, you're looking at the global state, right? So it seems obvious to you that you'll get V2 or V1 here, right? So it seems like it's predictable, right? In real system, it's not even predictable like that because nobody's observing the system and saying you should get that, right? It depends on when these events happen to show up on the system. So you can't really guarantee anything, right? I mean, so wait till you read the next paper, right? Then you have to say what you really saw here was a serial order, right? And it'll do a last writer wins on the serial ordering of the processes, right? Not on the time that you see. So if you explain this to the secretary, you have to say, assuming that this node would send this communication to the server and this causal ordering from here to here, right? Which is what you have to say, right? Because otherwise, so you can be guaranteed that if we are both operating on the same file, where you operate it on Wednesdays, I operate it on Thursday, it's easy to explain. But if you're both operating on the same, if you're both sitting next to each other on two desktops and you're operating on the files, like the make example I was talking about, right? If you do make on one machine, try to use it on the other machine, right? Then there are challenges on how you see when you see this stuff, right? And the thing to explain, right? To going back to programming 101. And the first thing you want is, well, I can lock this program by writing something to the file system, right? But then you think about it, if you think more and more, you have to basically say, I need to write and then make sure I read, right? But that doesn't solve the problem. I mean, that solves the problem for some cases, but not for everything, because it depends on how long these things are, right? It depends on so it depends on other concept, because what might have happened here is, instead of I drew this longer than this one, right? But what might have happened is this was really actually shorter than this one. But this message took a lot more time to reach the voice, right? So voice is the one which cares about all the stuff. So even though you wrote it very fast, it didn't reach voice for a long time because of the way network messages are ordered, right? So your lock won't work because it depends on this timing, right? And then if you're in programming 101, your question is, how can I solve this? I mean, can I write it faster and faster? And the answer is no, you can't. I mean, there's nothing to do with how fast you can write. This has got to do with the ordering, and maintaining order, creating order is extremely hard. And that's the message from the next class, right? So one way to look at this is it does a good job of giving you good performance, right? It's a clean way to implement inherently very hard problem, which is how to do stuff concurrently, right? This is one way to solve this and where you get good performance. I still don't believe that this is what would be intuitive to user, right? I think I still buy the argument that this is a reasonable solution to a very hard problem that we can't really solve it any more elegant way. There's no way to solve this problem which doesn't involve making things complicated, right? You can send a lot more messages to make these things complicated, but this is a simple, elegant system. So why would you choose this system? What is the factor of the Berkeley study which convinces you that this is not such a bad idea? Why are we not complaining? I mean, if you think about this, the first time I heard about this, my intuition was, why would anybody use AFS, right? Because it basically says that if two people are modifying a file, what you get at the end depends on pure luck, right? In the lines, I see different lines, but essentially what happens is whoever gets to the server last wins, right? So it doesn't matter what you do, but when the server gets the content, whoever gets the last wins. So, right? But obviously I was wrong because people continue to use AFS, right? Has anyone faced one of this stuff? And has someone faced like create a file kind of gone, right? I'm guessing not because none of you said you used it in a shared mode, right? So what gives? Why do we? Why is it still acceptable to use AFS? Yeah.
If you think about the Berkeley study, I mean, they're saying that most file accesses, they get a small file, they read it all really fast, and then close it, and then you're done with it. Mm-hmm. And so probably in most cases, well, first of all, in most cases, probably you're only reading. Mm-hmm. And in most cases, you do it so fast that it's probably a very rare event that two people are writing to a file at the mm-hmm. same time.
Mm-hmm. Yeah, essentially people don't share, right? I mean, that's at least the case here, right? None of us share this stuff, right? So if nobody's sharing, then why bother, right? So if you don't share, it doesn't matter whether this last writer wins or not. Like I said, for a single case, right? All you end up doing is you send the updates to the server, but nothing else. So if you have only one person operating on a file, AFS is very good because it'll give you the performance as a local files, except for the part that you have to upload the changes to the server, right? AFS is horrible if you want to do a shared system, right? Which in some sense is kind of awful because if you use the Berkeley study which showed that people don't share, and you build AFS, AFS is means that. Do you believe that you can actually write a shared application in AFS? I think one of the things they say is like they don't build a database, right? I think one of the reviewers from the class mentioned that that's the limitation of AFS, right? Can you build a database file in AFS, meaning one file that you modify to write a database, right? Where you modify, update, and all those things, right? The database kind of concept. Yeah.
Because there's only one server
mm-hmm.
daemon for the database that's running.
What happens if there's two?
Then you'll never work. I mean, you'll only write the database logs, so you can't use the file system to do anything with the database.
So yeah, explain more of what won't work, right?
So
if let's say there are two processes doing a database, right? There are two processes which are modifying the same file as a database concept, right? what would happen in AFS?
I mean, one of the processes would get to write to the transaction log, and some transactions may just disappear because if the other process is writing to the log, then when the other process writes over it, last writer wins, it will erase the transaction log from some common point, where they last broke off the read-only.
Yeah, any operation which are done concurrently is last, right? So you cannot have two people operating on the same file simultaneously, right? With this model, you cannot make that happen, right? So if two people want to modify it, right, you have to serialize it, right? Right? At a high level perspective, right? If let's say this is happening, right? This is case 1 and case 2 is, right? You have to use AFS in this model, right? Where updates from one process makes it through, and then those are incorporated into the other one, and then they happen, right? If you operate in this model where things are concurrently happening, then essentially what it means is that whatever this does is completely lost. Whatever this does is completely survives, or vice versa, right? It does not let two people modify the same file because the updates to a file are never sent to the server. Only the close is sent to the server. So whatever is happening here would not be seen by the other one. So you cannot build two processes to modify the same file because it's not possible to modify the same file, right? At the end, only one of the updates will survive, right? Because only the write is modified. So it doesn't matter what you do in the middle. Whoever writes last is the one which wins. There's no shared editing of a file. It's just not possible with AFS, right? You only modify the last one, right? How does it work in NFS? What's the NFS model? NFS does block level caching, right? So clients can download a block, right? So suppose you have a big file, right? And you have two processes on let's say different machines, right? They both want to modify the same exact file, right? So they both modify it, read it for write-only purposes, right? What happens if they, what would happen? So let's say this one writes 1 here, right? And this one overwrites as 2. Let's say these are blocks, right? And let's say this is what happens, right? Let's say this block only 1 modifies, this block only 2 modifies, this block 1 and 2 modify, right? What happens at the end? What is the sequence of events which happen?
If you write to the same block, then the last write wins.
Last write wins? Let's start from here, right? What happens for this block?
It's changed to whatever P1 writes.
So this one will win, right? And same for this one, right? Because nobody else is. So it is possible to modify a file. So at the end, the file that is left over will have contents updates from this and updates from this, right? What happens on the ones that both of them write at the same time? What does NFS do for writes? What does NFS, spike lead NFS do, and what does NFS do, right?
So standard NFS will just write the block, write, so one of them will win.
Write through, right?
Right.
So it'll do a write through, right? So there's no cache. So with NFS, the traditional NFS, you'll do a write through, so whichever block you route will be sent all the way through, right? There's no caching issues, right? There is a caching issue for a read client, right? Read client may have this block cache, so it may continue to see it for 30 seconds or so before you go back and ask the client, the server if it's still valid, right? The server does not know who's modifying a file, so if you cache the block, you may have it up to 30 seconds before it's flushed. But these two writes are always flush through, I mean write through, right? So if this one got lucky, it'll be sent. It's like I said, it's the last writer wins for the particular block. Guaranteed because it's write through. There's nothing, no caching issue here. The read users may see partial content, right? Because depending on how